As Casey said, my name is Bob Elwell, and I'm the president and owner of ProCAD Technologies. We're here today to discuss core shift, material degradation, and managing of multiple vendors, which is a unique problem with as we get into more complex projects. Managing the people and the processes become more difficult, and this is a project that we worked on a few years ago. As we said before, my name is Bob Elwell, and I'm the owner of a small engineering firm in Erie, Pennsylvania. We specialize in product design, mold design, computer simulation, and we specifically focus a lot on plastics and using Moldex3D. We work with all kinds of different customers, from OEMs, molders, tool shops, and anybody in between. And we kind of have a unique niche, solving problems that a typical toolmaker, tool shop combination, or maybe an OEM doesn't have the experiences and skills to solve. A brief outline of this project: we want to talk about the vendor involvement and how the vendors worked with each other, go into more detail of the core deflection issues that we found and the material degradation that they saw. We want to talk about the molding process, how the vendors ran their simulation to validate their processes. The molder still saw molding issues, and the vendors were not able to solve these problems. Then the OEM contacted ProCAD for additional engineering support, and we reviewed the problem, made recommendations to solve, and using Moldex3D's given us huge help to making this project easier to solve. We want to talk about the vendor involvement. Along with engineering simulation software, vendor interface is very important because you have mold builders, molders, material suppliers, and the like. You have to combine all these different kinds of people to come up with a good solution for the end customer. To go through this list of things that we had to solve, we wanted to start with looking for signs of material degradation near the gate. The core shifting in this project was about 50 thousandths. What was interesting about this project, though, the core shift was random. It went in multiple different directions, so that led us to believe that maybe it wasn't shear thinning and gate imbalance issues that typically occur in products like this. The molder tried quite a few processes over several weeks to try to fix the problem, and finally the molder got to the point where they had to call in reinforcements, and they called everybody involved with the project down to the shop to try and get this thing solved, and all the vendors were at a stalemate as to what to do next. So to take a look at all the vendor involvement in this, which is a critical part of this project, the molder, they had mold filling software, they had experience with the material, and they had a lot of experience with this OEM for several years, and they knew pretty much how to handle things. The mold builder, they also had very good reputation for building molds. They had mold filling software, and they've built unscrewing molds before in the past, and they were quite good at it. The manifold manufacturer was typically one of the big 5 or 10 that are out there. They had obviously good experience with valve gating. They had experience with this plastic material specifically, and they also used mold filling software. The material supplier obviously have been producing this material for quite some time. Admittedly, it did have some difficulty. It was difficult material to run, but they had lots of experience with it, and they also used mold filling software to validate any problems that they might run into. So let's start off with the molder and what they had to work with. The molder spent several weeks trying to solve this problem, varying processes, heats, mold, reviewing the press, the barrels, the whole 9 yards. They went through top to bottom trying to figure this out. They tried eliminating the degradation via process. They looked at trying to change velocities and things, trying to get the core shift to a minimum. The molder used up so much time trying to debug that they started to make the OEM potentially late on their shipment to their customers. And so the vendor kind of panicked and called in all their vendors for technical support. The molder reached the conclusion that, well, since we processed everything within normal limits, it can't be us. It's got to be the material or the product design, the mold, or the manifold. Moving on to the material supplier. They knew that the material it could be a little bit tricky to run. They also ran through their mold filling simulation. According to them, everything should be fine and run within acceptable limits. The supplier had molded similar parts before and knew that it was going to work fine. The mold supplier or the material supplier came into the molder and helped them process the press, and knew that they were running it within normal limits, and the supplier approved the molding process that they ran. So the material supplier walked away with concluding the same basic thing: well, it can't be us, it must be the mold, the manifold, or the press. All right, moving on to the mold builder. The molder picked this mold builder because it had a good reputation. They had them design the mold. They built the mold as they designed. They inspected the mold before shipping. They watched the mold sample at the molder with the material supplier and everybody else involved. And when they started running into problems, they pulled the mold out. They had the whole mold re-inspected. They determined that all the cavity steel was within 1/1000th of an inch. All of the issues were, or the cavity and the core steel were concentric, and therefore they shouldn't be seeing the core deflection that they were seeing. And they just determined that the mold was to print, and there was nothing else that they could do. So therefore, again, the mold, it can't be us. It must be the material, the manifold, or the processing. So moving on to the material supplier. The material supplier has built many of these types of manifolds in the past. They've had experience with valve gating. They've run this material before, and they've run similar parts, similar shapes before. So they walked away with the same type of attitude that, well, it can't be us. It must be the product design, the mold, or the processing. So the OEM was kind of getting a little stressed about the schedule and wasn't sure quite what to do. He was getting conflicting information from the vendors as to how to solve the problem. The vendors recommended that they thought that because the pressures were so high that the wall thickness was too thick or too thin, and they wanted to thicken the wall. The OEM scratched their head knowing that they've had parts at this thickness before with no problem, so why was this part a problem? So they contacted ProCAD Technologies looking for extra engineering support. So in discussing this with my customer, they concluded that they're running out of time, they couldn't meet the schedule, they weren't solving the problems, all of their vendors were not solving the problems, and it just seemed like the molder wanted to blame the OEM product design, looking for something to pin the problem on. And so they contacted us to evaluate, and they recommended to us that we look at thickening the wall. So we forwarded us all the material data, and so ProCAD got involved with the project. So in any project, we want to look at the three basic pillars of any good product design. You look at the design shape, the material selection, and the manufacturing process. In this particular project, we had a material failure, and we looked at material degradation, and everybody felt that the material should work. And therefore, the material supplier is walking away thinking that, well, if they would process it right, it wouldn't be the material. Moving over here to the manufacturing process part of things, they knew that there were stresses at the gate, and they suspected that the wall thickness was thin because of that, but the OEM knew that that wall thickness worked for them in the past, and there shouldn't be a problem, so the product design shouldn't be to blame. Moving down to the processing side of things, they knew that the manifold and the mold cavities were concentric, so the core deflections should be centered. They couldn't explain why they were seeing core deflections of up to 50 thousandths. So taking a look at the pressures, they knew that the pressures were higher than predicted, and that they couldn't explain that, and felt that that might be adding to the core deflection problems. So ProCAD took this layout of this flow chart of the design, material, and process, and we wanted to try to duplicate what they were seeing. So we looked at the material validations. And so step one, we wanted to check the current wall thickness and try and find out if we could see the pressures and stresses that they were currently seeing. Step two, we looked at the design side of things. We wanted to run a small DOE, varying fill time, pressures, and stress, trying to see if we could duplicate that side of things. And then we wanted to verify the process and look at the core deflections and see if there was any way that we could duplicate 50 thousandths deflections. And then once we captured all of that data, we were hoping under step four to determine what was causing all of this. So we took that flow chart and put it into an action item situation here. We looked at step one again to evaluate the current design. Step two was to try to run this process at extreme levels to see if we couldn't duplicate stresses and pressures. Step three, we wanted to try to verify and duplicate the core deflections, which seemed to be very evasive. Step four was to determine root cause and make sure that everything, the pressures and stresses were well within limits. So starting off with step one, we tried evaluating the stress, pressure. We wanted to consider the OEM recommendations of thickening the wall. So we started running the analysis, and we looked at the current wall, the gate, the material, and the processing. And we concluded that everything was okay. We could not find why this product was failing. It made no sense to us at all. Everything was in normal limits. Even the pressures were substantially lower by about 30 to 40%. So that really got us to scratching our heads, so that when we went to step two, we wanted to run our DOE to try to see if we could duplicate those stresses. And so we started out, the default was 2.2 seconds. And again, the pressures and stresses were very low. So the only way for us to achieve that was to, first we doubled it and then we quadrupled it to try to get the stresses and pressures up to where they needed to be from where the molder was at. We could not duplicate any of it. Everything came back well with, this design was pretty much bulletproof. Even though it was a difficult to mold material, we couldn't get it to break. So we concluded that the FEA, we couldn't duplicate any of the pressures, the stresses, the core shift. Couldn't see anything near the molder's pressures, and we couldn't duplicate any of the problems. So we went to step three, and we wanted to take a look at the core deflections as to what kinds of pressure differences would cause these deflections. And so what we did was we just took, in our stress analysis software inside SolidWorks, we applied a load to this core, and we kept increasing the loads until we got, now this load, this PSI, was uniform. We just cut the core in half and applied half the load. And we reached 4,000 PSI before we could get the core to bend 50 thousandths. And we noticed that according to the current design, the stresses on that steel were very high and most likely were going to crack. So again, this also seemed impossible. So everything on this project that was wrong, we couldn't verify at all anywhere. So we walked through the whole process and we reached these conclusions. We couldn't get the material to degrade. Even degrading at 4 times the filling speed, it still was fine. Core shift seemed unlikely to get up to the 4,000 PSI mark. We couldn't verify the high pressures, and basically we concluded that there's nothing wrong. So instead of finding problems, we found solutions. We went back to our OEM and told them that it wasn't the part, it wasn't the material, it wasn't the gate, and it wasn't the cavity. So therefore the problem was outside of the valve and outside of the cavity steel. So another way to flow this out was the product's not the problem, cavity's not the problem. So therefore the only thing we could come up with was it was either something in the press or something in the valve was stuck and the valve wasn't opening totally. And somehow the unscrewing components, we didn't really spend a lot of time working on the mold design side, but looking at the drawings, it looked like the design bearings and things like that in the unscrewing mechanism looked a little bit weak, and we felt that maybe with a little bit of core shift, it may have caused the unscrewing mechanism to tilt. And since the valve might be partially closed, the higher pressures that were required would force that unscrewing mechanism to tilt. So we took this information back to our OEM and helped him present this back to the molder and showed him the affected areas and how things are going. So he went back internally to his processing people out on the shop floor. They reviewed all the press equipment and processes, and they finally discovered that one of their hydraulic hoses, for whatever reason, was clogged or damaged and causing the valves to not open totally. So they fixed the hose, and the pressure and degradation problem went away instantly. There was still a little bit of core shift after that, and the mold builder went back to their shop and took a look at their mold design and discovered some inefficiencies with their design, and they had to redesign it and stiffen things up, and they were able to reduce the core deflection from 50 thousandths down to like 5. So ProCAD's conclusion of this whole process, which was quite exhausting actually, trying to chase this non-problem actually. The OEM purchasing department wanted a single source buying process so that they could hold everybody accountable, but in this particular case it didn't quite work out the way that they wanted. The vendor self-identification isolation, meaning that each person, each group of suppliers just basically worked in a silo and wanted to blame the other guy. There was a little bit of design and manufacturing paradigms. Because these guys had a lot of experience, they counted on their experience to get through, and they skipped some things. So the vendors didn't solve the problems. Assumptions were made. They skipped some steps. They didn't check the whole process. And it kind of gave some of the vendors a little bit of false confidence because they've done it in the past. They figured that this would just fly right through. And they spent a lot of time blaming each other rather than reviewing information in their own areas. So the OEM was running out of time, and he had no choice but to, instead of putting pressure onto the vendors, he had to get some external people involved. They contacted us to come in, validate the process, and then we made our recommendations.